Hey everybody, welcome back. I know that last video was a little bit long. The main thing I want you to remember though is this table, okay? So what are these 5 quantum numbers that come up from application of Schrodinger's equation and the addition of this spin of the electron, which came from, again, not application of the Schrodinger equation, but experimental observations. So there they are right there. Let's again talk about what would be allowed quantum numbers for a particular state. We only have to worry about 4 of the quantum numbers because the one that quantizes the size of that spin angular momentum, that little s, remember, is fixed at 1/2. So a collection of n, l, m sub l, and m sub s are going to determine a particular state of the atom. Okay, if we're focusing on the hydrogen atom, the state of the hydrogen atom. Okay, but generally, any atom is going to have this set of quantum numbers. Okay, now I am going to say one more thing before we look at possible combinations. We are ignoring something here. So this is really a simplification somewhat. We're ignoring the interaction of the spin of the electron with the orbiting of the orbit of the electron. And what I mean by that is, if you think about it, right, a charge going around orbiting is going to produce a magnetic field. Remember from physics 2, currents produce magnetic fields, so the electron going around produces a magnetic field. The spinning of the electron also produces a magnetic field, right? It's a little magnet. So there is an interaction of the spin magnet with the magnetic field produced by the orbiting electron. That's known as the spin-orbit magnetic coupling. If you include that, you have to edit or update this list of quantum numbers, because what happens is you get a total angular momentum, and that's usually symbolized by J, capital J. And it's that total angular momentum that actually ends up being quantized with a quantum number little j and a little m sub j, okay? So the principal quantum number is still there, but you have to include the total angular momentum. Okay, so if you include this spin-orbit magnetic coupling. So we're just going to neglect that. So our set of quantum numbers is a simplification, but that's okay. The idea that there are quantum numbers that define a level, or I should say a state, is what we want to get across, okay? So that complication, if you take physical chemistry or quantum mechanics, a physics course, upper level physics course called quantum mechanics, you'll talk more about that spin-orbit magnetic coupling. But let's just go with these 4 quantum numbers then. Again, remembering that S is a 5th one, but it's always the same value. So again, a combination of NL, M sub L, and M sub S will define a state. Now remember how the quantum numbers L, M sub L, and M sub S go, right? Quantum number L depends on the principal quantum number N, and M sub L depends on the value of L. M sub S can either be plus or minus 1/2, okay? So, as you see in this example, right, how many states would there be if the principal quantum number N is 2? Right, so you could figure that out. Let me go to my notepad and we'll do some figuring, okay? So, if n is 2 for this particular state, right, how many actual states have n equal 2? Well, okay, so we could have L starting at 0, and it's going to go up to n minus 1, so L could be 0 or 1. But for each L, M sub L, remember, is going to go from minus L in integer steps to plus L. All right, so let's start listing them. And then M sub S, remember, no matter what N, L, and M sub L are, M sub S can be plus or minus 1/2. All right, so if we start labeling these, Let's start with 2. And let's first do the states where L is 0. So we could have 2, 0. Now, if L is 0, what is M sub L? Well, the only value that M sub L could be would be 0, right? Because if L is 0, we started 0 and ended 0. So we would have 0, 0. But then remember, we could have plus 1/2, but we could have the same first 3 quantum numbers and a minus 1/2. Okay? All right. Now, we could then have L equal 1. All right, so we could have the state 2, 1. Now, what are the possible values of M sub L if L is 1? Well, M sub L could start at minus 1. Plus 1 gives us 0. Plus another 1 gives us plus 1. Oh, so we could have 3 possible values of M sub L for L equal 1. So these states would look like 2, 1, and I'll go with minus 1 first. And then we could have plus 1/2. But we could have 2, 1, minus 1, minus 1/2. But then we could have 2, 1, 0, plus 1/2. But we could have 2, 1, 0, minus 1/2. And then we could have 2, 1, 1, plus 1/2. And 2, 1, 1, minus 1/2. So for principal quantum number n, we have what? 1, 2, 3, 4, 5, 6, 7, 8 possible states. And if you keep doing this, you'll find out that for a given n, there will be 2n squared possible states. Now, the energy of these states is going to be determined by the principal quantum number 2. So in our simplified model, where we're ignoring spin-orbit interaction, there are 8 states that would have the same energy. States that have the same energy are called degenerate. I know, it's a funny word to use, but they're degenerate states, okay? But again, in practice, because of spin-orbit coupling, these states, the degeneracy will be removed for some of these states. So there'll be this what we sometimes call a fine splitting, and there's even a hyperfine splitting of these states, the energies of these states. And then if you stick the atoms in external magnetic fields, right, you have another interaction with that magnetic field. Okay, so all of these interactions, these magnetic interactions, can cause splittings of the states, of the degenerate states. Okay. The M sub S, and we're going to make some connections to physical chemistry now, stuff you probably talked about in chemistry. If M sub S is 1/2, this is sometimes known as spin up state. If M sub S is minus 1/2, this is known as the spin down state. So I know you guys have heard that terminology before. Okay? All right. In fact, speaking of chemistry, what I want you guys you may recall this, and this is on the next page of the summary notes. There's what we call spectroscopic notation or chemistry notation, and the principal quantum number is given a capital letter depending on its value. So n equal 1, that's sometimes referred to as uppercase K. Uppercase L is n equal 2. Uppercase M is n equal 3. The little l, the orbital quantum number, if L is 0, that's referred to with a lowercase s in this spectroscopic notation. L equal 1 is P, L equal 2 is D, L equal 3 is F. Now this might start to sound familiar, right? Yeah. In fact, the principal quantum number determines what we call the shell, right? The electron shell. The L value determines what we call the subshell. And then together, if you take the N, L, and M sub L, that determines what chemists call the orbital. All right, so this is starting to ring a bell. And here's what I want to now emphasize. Where these terms, shell, subshell, orbital, are coming from are, if you look at the actual eigenfunction. So if you look at these psi's, right, of r, theta, and phi, if you square these, this forms the probability, right? Density functions. You can actually integrate these, right? And say from over certain volumes and talk about the probability of finding the electron in a particular section of space. Now, if we start plotting what these probability densities look like for different states, you'll get something that looks like this. And I think this will ring a bell. Look over here. Can you see over here? Oh my goodness. Yeah, these are the electron clouds that you talk about in chemistry. Electron clouds are nothing more than probabilities of finding the electron. And these are shaded where you see the yellow shading, right? That's a very high probability. I think you'll recognize what chemists call the orbitals, right? And the subshells and then the shells. In particular, you can see the orbitals. Okay, so remember for L equal 1, so L equal 1, remember if you look at our spectroscopic notation, L equal 1 is known as a P subshell, right? And depending on the value of M sub L, you'll get different orbitals. For a P subshell, M sub L can be -1, 0, or L. Well, that forms, you might remember those dumbbell-shaped orbitals. Yeah? Yeah, that's what you see right here. Okay, you see right there? That sort of dumbbell-shaped. Sometimes you'll see this trace as, all right? Instead of shaded like that, you'll just see the outline of that orbital. So that's that P orbital where M sub L is 0. Okay. Anyway, here's the orbital where M sub L is +1, and here's an orbital where M sub L is 0. Okay. The S shells. So going back to here, right? S is L equals 0. Those subshells, I should say the subshells, those are spherically symmetric. They're spherical subshells, right? So those probabilities, if L is 0, there's no angular dependence on the probability of locating the electron. So if I go back to these pictures, like here's a 2, 0, 0, right? Orbital, actually. You can see it's spherically symmetric. Now, if you look for the 2, 0, 0 subshell, you're very likely to find the electron in this region. Very unlikely, very low probability in finding the electron here. And then an increased probability of finding it out here. But, I mean, I could go on and on about this. I'm just trying to make connections to what you guys talked about in chemistry. So those electron clouds are really probabilities. Okay? So a state, right? NL, M sub L, and M sub S either being spin up, spin down. You can also talk about the probability of locating the electron, which is these subshells, orbitals, and I should say these orbitals. Okay, that's the lowest level. Okay, now another thing I want to talk about then, which harkens back to chemistry, is what's called the Pauli Exclusion Principle. And what different ways to state it. And Pauli actually stated this. You can't really derive this from quantum mechanics, but you can show that it's consistent with quantum mechanics. Okay, it's pretty neat. And one way to say the Pauli Exclusion Principle is that no two electrons in an atom can have the same set of quantum numbers. Equivalently, no two electrons can be in the same state. Okay, so if you think of the hydrogen atom, right? Note that electron has to be in one particular state. Okay, no big deal, one electron. But you start to get multi-electron atoms, no two electrons can have the same set of quantum numbers. Well, this is going to explain, right, the whole idea of how you fill these orbitals with electrons, right? You guys remember doing this in chemistry? Yeah, don't worry, I'm not going to make you do it. But, you know, for instance, For instance, if you do like, oh my gosh, I'm trying to remember. Let's do carbon, right? I know that carbon, right, has 6 protons. So neutral carbon would have 6 electrons. So you can start to do that electron filling. So you would go, okay, like remember the 1s? So that's quantum, principal quantum number, right? N, and what does the S refer to? The S refers to L equals 0, that subshell. So how many electrons can you get, right, in this subshell? Well, let's see. What are the possible states in terms of quantum numbers for n equal 1 and L equals 0? Well, if we think about it, right, if n is 1 and L is 0, the only value for m sub L is 0 based on L equals 0. And then, of course, we have spin up, spin down, plus or minus 1/2. So there are two possible states in the 1s, right, subshell. So the most we can get in that 1s subshell are going to be 2 electrons, because no 2 electrons can have the same set of quantum numbers. So I have to take care of 6 electrons for carbon, so the most I can fit in here is 2. All right, then what do we do next? Well, then we go to the next subshell, right? So what's that going to be? I guess that's going to be, in terms of energy, that's going to be 2s. Okay, so how many can we fit in the 2s? Well, again, that's going to be 2, 0. The little l equals 0 is s, right? So m sub L is 0. So we have plus or minus 1/2. So the most we're going to be able to fit in here is 2. Now we've taken care of 4 electrons. Now, what's the next state in terms of energy? That's going to be 2, right? Little l equal 1. Okay, and then we could have, well, they're up here. How many states do we have there with 2, 1? Well, we have this one, 1, 2, 3, 4, 5, 6. So there are actually 6 states that will have n equal 2, L equal 1, and that spectroscopic notation for L equal 1 is the P, right? The P subshell. Well, we can get up to 6 electrons in that one because there are 6 possible states, but for carbon, we only have to worry about 2 more. So that's what the electron filling would look like for carbon. You guys remember doing that? Yeah? So the Pauli Exclusion Principle, no 2 electrons can have the same set of quantum numbers. Yeah, that's consistent with how electrons actually fill these orbitals and subshells, okay? And that whole filling of the orbitals and subshells, that explains the whole organization of the periodic table. So all this stuff now, right, is consistent, and now we have this quantum mechanics, this theory, that's giving us a theoretical basis for all this stuff that historically has been observed and empirically, right, stated. And the periodic table, of course, was built long before quantum mechanics comes along, but everything is consistent now, okay? All right, again, don't worry, I'm not going to make you do electron filling and bring back nightmares of chemistry, but I wanted to mention that. Okay, any other notes? Because I know I'm blabbing for a long time here. Just stick to these summary notes in terms of what you should know. Yeah, that's all I want to say. Okay, in the next video, we'll actually look at X-ray production. Now that we have the whole idea of atomic states, and not just for hydrogen. Remember, this also applies for any atom. Now we are making some simplifications again, ignoring spin-orbit interaction. That's okay. But now that we have the whole idea of atomic states, I want to say a little bit about X-ray production in the next video. Okay, see you in the next video. Bye-bye.